Welcome everyone to our high energy physics seminar at McGill this week. And today we're very happy to have Sabrina Gonzalez Pasterski from from PI, I think, or Princeton, depending on what's how we define where. And she's going to be talking about a shorter path to celestial currents. So please, Sabrina, go ahead whenever you want.
Hi, so thank you guys for having me. I guess I'm not even putting my affiliations on my slides because I'm not sure where I want to say I am. But so I'm happy to be talking about this paper with archive number down here. And then also some of the comments, of course, are going to be building up a lot of work with collaborators coming out of Andy's group and I remember Linde, and some upcoming work with Sebastian Mazura at IS should appear soon and have some relation to some of the things here. Okay, so basically, celestialography proposes a duality between there's gravitational scattering or S matrix with gravity in asymptotically flat space-times and a conformal field theory living on the celestial sphere. And so basically, whenever I use the word celestial amplitudes, I'm going to just be talking about S matrix elements in a basis where they're transforming as correlators in D-2. And so the point of this talk is to go through a particular aspect of the motivation for this program that kind of highlights, I guess, why this presentation of scattering might be taking better advantage of available symmetries. And I think that there's kind of two notions of this that have come up at different times in this timeline here. And that's kind of going to be what we're kind of going to unpack a bit. So basically, the main motivation for why we're changing this basis, so this is a very rough timeline just to kind of get some of the highlights of what people were doing and how it's connected, but it all seems like you're doing the same thing for a long time, but there are different interesting outputs. So let's just start with the beginning here. So basically what was happening is that there's this connection between soft theorems and word identities, and then relating those soft theorems to basically treat them like they're currents living on the night sky. And so that is what motivated essentially changing the basis over to looking at boost basis for all energy, so all external particle states. We're going to look at a boost basis and understanding various aspects of this proposed dictionary that I'm going to go to in a little more detail in a couple of slides. But basically, this is one set of infinities of symmetries. And this is a set of, I guess, infinities that you get only in a 4D bulk and a 2D boundary, because it's essentially like their local Laurence transformations being promoted to a Virasoro symmetry, for instance. So the first, I guess, impetus for this program, you hear a lot of Andy saying, oh, look, there's an infinite number of symmetries. Let's try doing it in a way that takes a better account of them. And I want to point out, though, that there's kind of been another kind of notion of an infinite number of symmetries that maybe is more interesting, or at least it's newer, and people are trying to explore the impact of it more recently, which is this W infinity symmetry that you've seen also Kevin's work, but Andy and his collaborators' papers about maybe a year ago or so, talking about how if you look at a single helicity sector of scattering in a celestial basis, you see naturally these generators of a loop W infinity algebra. So that kind of spans this arc of the things that I've been talking about today. And essentially what I'm going to be presenting, or the title of the talk, is focusing on a kind of shortcut here. And it uses a perspective that takes very seriously this notion of Rindler time evolution. And we're going to see that how far you can push it might more naturally give you this W infinity than maybe the original setup looking at asymptotic symmetries to try to find these 2D symmetries. Okay, so synopsis for the talk, because bullet points to make sure that I don't ramble. We're going to present a streamlined route from asymptotic symmetries in 4D to currents living on this 2D celestial CFT. We're going to use this to re-examine the bulk picture of radial evolution in the 2D theory. So in the first part of the talk, there's going to be a lot of emphasis on just looking at celestial amplitudes and properties of them, because in the end, we kind of want to abstract away these kind of questions of whether or not these asymptotic symmetries are physical, what to add to that and whatnot, just focus on what is in the amplitude. And so basically then when we lift that back to the bulk, it's important to understand how tools from radial quantization and celestial CFT that maybe we've taken granted, or basically taken as something we can do without thinking too much about what that would mean, what that means in the bulk, and kind of how we're actually treating this hologram compared to maybe what we're used to in ADS CFT. So that's going to be kind of the emphasis here, even though a lot of the slides, maybe if you saw it at strings out, I do say a bit about what celestial amplitudes are, et cetera, et cetera. This is going to be a bit different. Okay, So the next thing is that basically this route is going to make the relation to quantum field theories off the theorems manifest just from the way that we're slicing the Vulcan boundary. And we want to reconcile basically the construction of charges in celestial CFT with our more familiar notions of a hologram in ADS CFT, where basically the codimension is only 1 versus now the codimension is 2. So what gives? And basically the point is that when we look at massless scattering from different points of view, so just from the S matrix or from boundary correlators on null infinity or the celestial basis, we're going to try to turn around what we've talked about before to see kind of why the celestial framework has like certain advantages, or why one maybe in hindsight would want to really chop up the bulk of the boundary in this way. Okay, so outline is as follows. First thing is just to try to go from basically momentum space to position space so that we can then focus on momentum space for a little bit to set up the 2 types of infinite number of symmetries, which is the ones that I first talked about, which is the stress tensors and the other like soft theorems that we've known for a while, and how they give basically enhancements from global symmetries to local symmetries, like or organized like a local 2D CFT. But then also the W infinity symmetry. So the 2 types of symmetries are going to come from basically kind of extending the construction for the leading soft theorems to a full tower. And we want to basically understand why both of those are natural from this boost basis. So then we're going to follow this boost basis and think about what that means in space-time and go through a particular U1 example, which is the one that's highlighted in the paper. That's the title of the talk. And then finally, we're going to come back to this flat space hologram that we kind of set up with this boundary correlator picture, and then discuss the different ways that we've sliced the boundary in bulk. And again, kind of the argument for the celestial advantage and the kind of questions that actually are still a little bit open, or at least need to be just worked out fully to basically appreciate, I think, somehow certain kind of steps that one needs to do to reconcile like what's different about the celestial CFT and normal 2D CFTs or the ADS CFT analog. Okay, so our goal again for this program is we have lambda equals 0, quantum gravity. We want a hologram for it. And the proposal is that this hologram is naturally living codimension 2 on a celestial sphere. So again, this class of spacetimes is asymptotically flat. That means that I have localized stress tensor sources, and it means that osmotic constant is 0. So my metric will no longer be flat. It will have some sort of perturbations of it. Well, not just perturbations, but basically at infinity, it's going to asymptote to being flat again. Okay, so the main thing for when I talk about null infinity or celestial sphere, we want to make sure that that phrasing is established here. So basically, you have this Penrose diagram, and the conformal compactification of Minkowski space or asymptotically flat spacetimes without any black holes will have these boundary components. The point is that the interesting thing about Minkowski space is that you have basically 2 null components for where radiation, so massless fields would, the initial data would enter and exit the space-time. So that's going to play a crucial role for, I guess, how we would think about how the massless excitations in the bulk really should be captured on a hologram. And so essentially, we're going to have this data at null infinity be capturing our Cauchy data. And so if I have a massive excitation, I also need to worry about what happens at time like infinity. And those are the 2 here that I would resolve with a hyperbole. Robert had a question?
Yes, I have a very simple question. Yes. I thought that Minkowski was only half of this Penrose diagram.
Yes. Oh, yeah. I did. Okay. So I have a bad habit of doing this because I want to visualize something later in there. Okay, there's 2 reasons why I do this, and this is maybe not a good thing. So the first thing is that basically when Andy would use to double this Penrose diagram, he would want to emphasize that there's a antipodal matching condition here for the charges across spatial infinity. And for me, why I like to double it is because I want to really think of cutting this kind of diamond, which I guess is easier to visualize for a like 1-dimension lowercase. I guess you could have like a circle coming out here, cutting it with a hyperplane. And seeing how the hyperplane, before you've done this weird warping of the conformal compactification, actually intersects this null boundary. And so I'm going to open it up like that, and I'm going to try to like extrude it out in 3D, which is not really a Penrose diagram then. So forgive that aspect of it. But the point is that here, I'm just emphasizing that like I have basically now 2 points in the celestial sphere here, mapping to like say north and south pole of this celestial sphere here. So this cross section. Okay. I'm going to basically look at a configuration where I really want to think about the north and south poles and like the rim horizons there. So that's why I've doubled everything and I stuck to that. But I agree the normal Penrose diagram would just chop off the left-hand side and basically say I have an S2 fiber over every point instead of this like like 2 points in this too, because I've opened it up. So that's all. Is that fine?
Sure. Fine.
Great. Yeah, no, but I guess that's good for pedagogy. Like, yeah. Okay, so I've butchered, or I've made that assumption so long that I don't even think about it too much, but I know I've been called it a couple of times. So let's emphasize that. And basically the point is now I'm going to call the celestial sphere that cross section of sky. Okay, so now when I want to think of two precedents for a flat space hologram, I have maybe two natural ones. One of them is just thinking about the fact that the S matrix is already a function of on-shell data. And so there's a sense in which if I understood, maybe you would want a more space-time interpretation of that S matrix, because basically as this abstract function of on-shell data, if we could have a theory that defines like how that thing behaves, that would kind of be like a hologram in the sense that at least the codimension is right. But obviously it's hard to think of like the notion of like whatever causality or locality in this space. And so maybe the more natural precedent for a hologram would be some sort of flat space limit of ADS CFD. But then again, when you turn the cosmological constant on, if this negative sign, you have a system in a box. And so the question of like null infinity here and like the fact that you're allowing radiation to go outwards is a little bit the origin of how it's kind of been a challenge for people. Like I think Compare and others have looked at this too, and there's various other like flat space limits of ADS to get S matrix elements. How we want to, I guess, understand how to go from this type of causal structure to the standard causal structure, maybe embedding Minkowski space in some sort of small region of ADS CFD, for instance, because the curvature scale is supposed to be going to 0. So essentially, like those are the two precedents I have in mind, and at least the like kind of the thing that remedies the two is we can have a space-time interpretation of this S matrix, and we do that by just basically taking a Cauchy slice, pushing the Cauchy slice to the far future and the far past, making sure that we're actually hugging the conformal boundary. And so for basically massless scattering, I really can just worry about the contribution near sky minus and sky plus, even though for massive cases, I need to care about I minus and I plus. I have now just taken my, my bulk fields and push them to the boundary, and I can prepare a state that way. So to be a little bit more clear about that, if I take a saddle point approximation, so I have a free theory, first of all, and I have my just plane wave mode expansion for the graviton, say, then these plane waves here, if I take the limit that R goes to infinity and U is fixed, essentially this part of the phase is very rapidly oscillating, so that large R limit, assuming that that the energy isn't exactly 0 right now, will basically, I like want to localize this term to where the point on the night sky is aligned with the momentum of that particle. And so what I end up seeing is that from the point of view of this kind of Penrose diagram, like, or some like bastardization of the Penrose diagram, I have essentially that a given frequency. So if I'm at this point here, I have a null direction and a given energy for my momentum, that guy is now basically an operator smeared along the generator of scry with a plane wave phase. So I can think of my S matrix elements instead of like an LSD formulation as basically a correlator in 4D of a bunch of operators smeared along generators of scry, which are basically the boundary limits of the graviton or the boundary limits of like the gauge field. And so this is the picture that I want to view the S matrix as. And it's nice because there are certain elements of, well, at the very end of the talk, I'll talk about some of the Carolinian story. And in that case, I think if you can, so long as you have this quantum theory of gravity in the bulk, but you have the limit near the boundary, maybe behaving more like a quantum field theory as opposed to whatever you have to worry about, like with the geometry in the bulk, that perhaps it's intuitive to kind of see that I really do have, like, say this region, at least near the boundary, where I have these local operators that I can use techniques for, like how correlators should behave, or if I insert a current, how it would look like, the word it needs to look like. So that's kind of a nice picture to have in mind. But for my purpose of the next part of the talk, I just want to basically say, I'm going to stick to the S matrix, look at properties of the S matrix. And then at the end, I want to lift it back up to see this picture where I think of each of those particles as being supported upon rays at null infinity. Good. Okay. So yes, question. It's a good time for questions.
Yeah, so I'm not, okay, so I don't work in this field, so maybe this is a silly question, but you're assuming this, basically the conformal compactification, at some point you're gonna find results, and are you going to like decompactify? Because to me, it seems that you're gluing two Minkowski space to do that.
Okay, so I would say, okay, I think that I am basically not quite So maybe you can clarify a little bit the two Minkowski spaces, because I'm not saying that I'm actually looking at the compactification. I'm looking at the limits. Basically, I'm using the conformal compactification to understand what limits I want to look at. So I agree that there's like singularities at I0, for instance, I plus and I minus. And the only thing that I'm saying is that I'm basically kind of looking at the patch where like R goes to infinity and then U is a full real line. And I definitely take advantage of those limits of the spacetime, but I'm normally using still bulk coordinates instead of thinking of like the canonical data at like Ashokar's type of.
So sorry, I should have said two asymptotical flat space, not Minkowski. Sorry.
Okay. Sorry. Can you clarify with the two there, because are you doubling it because of some sort of?
I think it's related with the doubling that you mentioned to Robert initially.
Okay. So maybe if you have a good reference for where I can understand how it's treated more generally, because the thing is that for me, I definitely have two null boundaries. So maybe if what's your background in as far as a subfield? Because if you're an S matrix person or like some sort of like a flat space limit of ADS person, I could see where there's definitely a doubling just from what I'm mechanically doing, but I don't know if I understand why it had to have been there, if that makes sense.
So, okay, so you mentioned an S matrix. So this is made of, you have the in and out states, right? So it seems that both your in and out state, the asymptotic states, they include, let's say, states on one both, let's say, asymptotic flat space.
So the question, sorry, I guess the question is, I would say that there's a positive frequency modes and negative frequency modes, and I'm trying to manipulate orders of limits so that basically on this out surface, I have only one half of those, and then on the in surface, I only have the other. If I strictly speaking don't take that order of limits first, then I agree with you that each of these lines kind of goes all the way down, and so it's like it doesn't look as isolated between the two. And I think there could be something better said there if there is like a good reference for how you accidentally get this doubling, but I don't know if it's, I would say that from what I'm doing now, you will be able to track through every time where I've strictly speaking looked at order of limits and said I needed to take R to infinity first before I could talk about this null generator. But if you have a good reference for just where you're coming from, I'm happy to discuss that more.
Let's understand. Okay. I'll try to follow.
Yeah, no, please do, because I do want to appreciate something there's something along those lines. It's quite important for just, so we'll hopefully come up with something later that you can see that I rather think of this full bulk picture, never really be strictly at the boundary, but there is something, if you're not careful about order of limits, you do have support at both scry plus and scry minus. So this drawing is strictly speaking, I guess at scry maybe, but what I mean is just in the future, this top line. Okay, good. So I'm going to focus on the S matrix. And what I'm going to have is the following, is that I have basically my function of external states that are on shell. And I'm going to in the future basically focus on basically just the massless case for now, in which case I'm going to parameterize the momentum as follows. So there's a point in the night sky and an energy variable. Okay, so now Laurence transformations in Minkowski space are global conformal transformations in celestial sphere. And so when I choose to go to a boost basis, this is just a choice of wave packets. And so these guys transform as quasi-primaries, basically by construction. And for the massless case, it's enough to see this. So you have each of the external particles that are in some helicity representation. Basically, if I do a rotation around the momentum direction, those external states transform into the little group with that representation determined by the helicity. And then now all is basically by Mellon transforming out the energy variable, I'm giving it a weight for the conformal dimension too. So essentially I can create something which is just an integral transform of my amplitude, which is implementing a change of basis that now transforms like a correlator of quasi-primaries. And this is nothing, this is just a choice that I made based on the, I guess, Poincare representations of the external scattering states that I already had in momentum space. So one can worry about whether this integral transformation converges, et cetera, but this is a formal choice. And so at first, if I just kind of plug through, just taking that change of basis, my holographic map is going to need a continuous spectrum of operator dimensions for each bulk quantum field operator. So basically, that is a bit different from the normal ADS3 or ADS4 CFT3 case, in that now I really do have like a tunable parameter, but I'm going to use that tuning to my advantage. And so basically, I'm going to analytically continue from the principal series that would be capturing this equivalent amount of data to the complex plane. And when I do that now,
can I ask a question? Yeah. Sorry to interrupt.
No.
The fact that you actually have a continuous family of I don't know what we call it, scaling dimension eigenstates
Yeah.
for each particle. That, I mean, that's basically because you're going down 2 dimensions instead of 1 dimension. Okay.
Exactly. Yeah.
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 Right.
Yep.
Do you mind just flashing the previous slide again?
Yes, of course.
Yeah.
Sorry, I'm
Okay.
but yeah.
Okay, go ahead. And the one is there basically for the usual reasons that in ADS, yeah, that one is just there's some simple argument for where that one comes from, probably.
I think
it's
the simple,
just
I
like-
mean,
'cause
definitely
you've
just
got-
from like the Casimir of like
Yeah,
the box
Okay. Okay.
in 40 and then reducing. Good.
And
Okay,
the pluses and minuses on the operators are in and out.
in and out. Yep. Sorry.
And
So
so
I guess
the Mellin transform, would I go from 0 to minus infinity instead of 0 to plus infinity for the
it's a little
outs?
easier not to introduce a phase there, but yes, roughly speaking, like I think that we've tracked through like the thing that's more crossing some like 40 kinematic crossing symmetric, and you don't want to add an e to the I delta, whatever, but for the in and out, but basically, yeah, you're just changing the phase of the wave function here beforehand. So you can equivalently change the integrand here and maybe add a phase here depending on what normalization is convenient, but yeah.
Okay, thanks.
Great. Okay. Cool. Okay. So basically, the reason why I want to emphasize that we can tune this conformal dimension is essentially that there's just 2 aspects of celestial amplitudes that I want to focus on before I jump to the main thing that I wanted to play with today. And that's soft limits and collinear limits, because those are the key. So the celestial holography program, if it works out, it's going to be trying to bootstrap amplitudes from soft and collinear limits. And we can see this as follows. So we have this tunable value of the conformal dimension, which makes it so that it's not quite like you're trying to you would not try to bound operator dimensions. You would instead try to talk about, I guess, positivities of residues in these conformal dimensions or something like that's the structure of the setup would be more like that. And for instance, if I have a soft expansion, so if I take a amplitude and I have a gauge boson and I have a series expansion and its energy going soft, so this is a tree level expansion, there's no logs I've written down here, then I would essentially see that there's a residue in delta corresponding to each order in that soft expansion that I see, and it's going to be to the left of the principal series. And if I had now log corrections coming from loops, and so I'm still implementing an IR cutoff to have that expression written down, I would have multiple poles at those values of delta.
Can I ask another question just to make sure I understand correctly?
Yes.
So the amplitudes, when you go to this Mellin basis and you write them as functions of z and z bar with different values of delta, are they single valued functions of z and z bar? Because you now
they're
have
not
like
when you do certain soft. So I think
continuous dimensions. So that sounds to me like they're not single valued functions of z and z bar. Like how could they, like they have branch cuts and stuff like that.
They definitely do if you continue z and z bar to not be on the real locus. I think there's something. So what I mean by that, basically, like there's 2 issues that one runs into. First of all, there's these when you try to strip off IR divergences, you need to use vertex operators of these dressing operators that definitely have like log 2-point functions. So that's one type of funny problem. But I would say that I think that it's such that if you're strictly speaking on the locus, you stay on z equals z bar, then every time you go around another operator, just the spin affects like the phase there.
Sorry, if z is equal to z bar, how can you go around?
Not z equals, sorry, z star equals z bar. I'm so sorry.
I see. Okay.
But we are oftentimes going to complexify z and z bar, and in that case, yes, you can.
But if z bar is z star, the correlation functions are single valued functions of z and z bar. Because that surprises me because, oh wait, does it surprise me? I don't know. I'm not used to thinking about complex dimensions, but I would have thought that, yeah.
I don't
know. I'm just worried because like in a usual 2D CFT, you would have to worry about branch cuts.
So what I'm saying is when I move Z1 around Z2 and then I move Z bar 1 around Z bar 2, I thought the phases canceled between the two.
Okay, they do. So everything is single valued.
Sorry.
I guess that's quantization of spin or something like that.
Yes. Sorry. Okay. So that's what I'm saying. I know I obviously I said something there with the Z equals star, sorry, which is something that not relevant here. So so I'm just meaning that when I think that if I did the right phase prescription and I stayed on the celestial sphere, then technically speaking, I could cancel that. But I do think it's important because I do want to move off of that locus. So I'm not gonna, I don't want to say, I think if anything, hopefully we can find, like when you take Z and Z bar to be independent real variables, you're in 2-2, and there you would expect like a 1-1 CFT, and that you would have like like cones and singularities when you go around them. So I think I want to understand that structure and how it imprints on maybe these epsilon labels, for instance, the in and out.
I see.
Sorry, in
I
and out.
see. Okay, thank you.
But in strictly speaking, I think you can avoid it in 1.3. Okay, good. So soft limits give me these poles in delta. And then if I look at, for instance, the soft graviton and its expansion, I have a Weinberg pole here. And then Cacciazzo and Strominger found the subleading soft theorem. And so those turn into poles at delta equals 1, delta equals 0. And so now, basically, the reason why we would go to this basis at all is because essentially there is a candidate stress tensor coming from the soft graviton mode. And but what I mean is that I guess it's a shadow of a dimension 0 operator. So that's how it gets to be a 2-0 operator. It's basically this soft limit of the graviton smeared on the celestial sphere is defined to be the stress tensor. And that smearing is going to be a bit of a problem that we encounter with this, like what's the right basis where we can think of local operators in the celestial sphere, et cetera. And so we want to keep that in the back burner. But basically in this context, these quasi-primaries get promoted to Virasoro primaries when we turn on gravity. And that's the brunt of why we went to this boost basis, because essentially the way that the subleading soft graviton couples is through the Rindler energies. And so that's why this HK would be diagonalized if I am in these boost eigenstates. So that's why we went and boost transformed everything, or transformed to a boost basis for everything. Now,
HK is delta K minus JK.
HK is, yes, that's
or
right.
something like that.
Yeah,
Okay.
so HK is just 1/2 delta plus J, and delta is now the delta that I've transformed to. Which is these guys. Good. Yep. Okay. So now the second thing that I have at my disposal is, so those are how soft limits get mapped, and then collinear limits. So the collinear limits, again, and this is part of the subtlety with like, what
Sorry,
are the
and where did the Virasoro, sorry to slow you down.
Oh, no
Where
worries,
did the
yeah.
getting promoted to Virasoro primaries come from? Are you addressing, you're not taking some other state,
I'm
you're
literally
addressing
just
it with,
coupling to the soft graviton. So I didn't want
see.
to go into the derivation of the word identity, because I guess I feel like I've said the talk too many times, but I'm taking the soft theorem here, which is just, so I'm saying that the residue at delta goes to 0 picks out this mode that has this coupling to each of the external states. So it measures their angular momentum. And now essentially, if I take that kernel here, so this is like the PK or the external momenta, the Q is the soft momenta, which is just giving me the direction of the night sky, basically, and I smear it, then that soft theorem looks like a T hard operator OPE. So mechanically speaking, I'm just transforming the soft theorem in this way.
Maybe just to be make sure I understand. So the stress tensor is the subleading term, and
the stress tensor is the subleading soft graviton, which I basically I wrote it here only in terms of A's and A daggers because I wanted to just talk about the amplitude, but I could have also just written it in terms of like a U integral.
Yeah, good. Yeah, because the leading term measure for the energies that would be.
Yeah, so the leading term is the super translations, and so I think the more natural way here is to think of like super rotations, and then global translations give you super translations or something. But yeah, so this is yeah.
I see. And just so the fact that these things are now Virasoro primaries, like the fact that they were quasi primaries was just some straightforward representation theory of SO31.
Yes.
The fact that they're now quasi primaries is the statement about how they transform under diffs that don't fall off.
Yeah.
Or that fall off in some specified way at infinity. Okay.
Exactly. Yes. And so yes, so that's the point. I guess one would hope that you get this stress tensor when you have gravity, but the weird thing here now is, of course, this is one particular mode of the bulk graviton, again because of this codimension business. And so what will happen in the next couple slides is we're going to get now not just the stress tensor as a graviton mode, but a full tower. So if one was very optimistic, one would hope maybe that these poles that I talked about in the soft expansion might be enough. Like you could maybe deform the principal series contour and capture a bunch of like data poles, and then that would be a more interesting 2D like system with maybe a finite tower. I mean, not a finite tower, infinite, but like discrete sum as opposed to continuous. So if that's nicer, but that's very speculative, and that's just to really emphasize here that basically before. And this is where the timeline is interesting, because basically the W infinity stuff is much more recent than the stress tensor stuff back in like 2014, 2015. And so just to emphasize that I think we're getting a little bit better understanding of this, of like what we want to expect from this hologram. So, okay. So next thing I want to say is that we had soft limits of scattering with these poles and I could interpret for you a couple of the residues and say, oh, look, there's this infinite number of symmetries, which is like Virasoro versus global. But now I have even possibly more. And I see that by looking at the collinear limit of scattering in this complexified collinear limit. And so this is again where I don't want to be too glib about like whether things are single valued, because I need to think of Z and Z bar as independent complex variables if I want to extract an interesting collinear limit from the graviton. And so when I do that though, I can basically pretend I'm doing radial quantization and say the Z variable and use that pole here to give me an algebra for these operators for the graviton. And so when I do that, I can basically mode expand the different residues in that tower and create Andy and Friends W infinity algebra. So what these are doing is they're computed from the OPE that one gets, and one can naively basically just literally, if you wanted to be an amplitude person, you could take the collinear splitting function, Mellin transform it to get this OPE in the celestial basis, and then now look at those a mode expansion of those operators. This thing terminates because the values of the conformal dimension are negative integers, and use the radial quantization commutator to get this algebra. So there's a small complexification here, which is like, I guess, a big caveat with in the bigger picture of how the celestial torus picture, celestial sphere picture all are mixed up. But the thing that I wanted to point out is that basically, okay, you had soft limits that we understood in momentum space. You have this, you know, that the conformally soft limits basically turn those into poles. And we expect now this full tower of poles where we can have interesting symmetry algebras. So there's, in that span of that timeline, there's really been two kind of notions of infinite symmetries. The first one is, okay, I couple to gravity, I have a Virasoro symmetry, not just a Laurence symmetry. That's interesting. Let me really push that further. And then when you push it further, you have what seems like a full tower. Now, of course, there's the subtlety here about how this W infinity, one element of the tower gets shadowed to a stress tensor and the other helicity. And that's like, and so they definitely, there's things that one can kind of tear at here, which are good questions. But I want to kind of, I guess, emphasize that basically going to the basis made you want to, I guess, try to apply CFT2 techniques to the thing. And basically the collinear limits treated like they are, like you can treat it like a radial quantized 2D theory, gives you this tower of symmetries that one can make sense of in a twistor space formalism for self-dual gravity. So I'm a single helicity sector looking at the OPEs. So just to point out two notions of infinity. Okay, sorry. Yeah.
Yeah, you call them symmetries. Like, in what sense are they symmetries?
So in the sense that there's this closed algebra. I don't know if you want to.
But like, does the Hilbert space of like soft graviton modes form a representation?
Yeah, I would say that. I think that's true. I think, or at least I think that of conformally soft modes.
Or is that only just when you have negative similarity?
Yeah, so I think that there is some debate about what to do when you add an, like, so basically we know that in single helicity sector, if you include like loop orders for like anti-self-dual gravity angles, I think that this is fine. There's various, I mean, so essentially these collinear limits should still be part of the algebra. So I guess once you add other commutation relations, maybe it doesn't close or something. I don't want to push.
I guess my question was much more naive than that. Okay, yeah. It's an algebra, but I mean, one thing that was special about the first few, the up to sub leading order in the stress tensor expansion is that they're computable from just the particles that go to infinity. Instead, they don't. They're very insensitive to the process in the middle. But when you look at these sub leading guys, they're very much sensitive about all the details of the process. So like I don't understand what is gained by calling them conserved quantities.
No, exactly. So what I want to say is, okay, there's definitely no global conservation laws, but this is this. Okay, so the only global ones you still have is Poincaré. But I think, so first of all, I guess there's two things. And so I didn't focus the talk on this, but I think you can get the W infinity from going like one more subleading order to the ones where you have this good asymptotic symmetry interpretation, and then you can shift the weights down with the commutators there. So what I would, okay, so let me, can I give an intuitive notion for what I think these two sets of symmetries are? There's if I have a static electric charge configuration, I can look at a multipole expansion of that object. The first notion of infinities here would be like looking at the monopole fields of a bunch of boosted configurations like that. Yeah. And then these W infinities are essentially probing those higher multiple moments. And of course, you're right that like you mix, if you say you only had dipoles and you had scattering where you never ionized anything and you only still had electric dipoles coming out, then one could look at a class where the first, say, in Amsoff theorem is identically 0, and then the subleading one is the first contribution. And I think that there's some region of scattering where that makes sense. One could artificially go more and more subleading order and try to construct these configurations. But the question is, of course, like once you have higher multiple moments in the scattering process, you're going to mix basically boost combinations. It's like the angular momentum, for instance, won't just be, say, like there's an orbital contribution or whatnot. You basically see this mixing of like the leading monopoles because they have some like impact parameter, give you a dipole contribution, etc. So I agree with you that basically you're right, that the intuition here is that the W1 infinities are going into the bulk. So like there's like basically integration constants when you try to solve the metric, when you go order by order and 1 over R, those subleading terms are essentially related to what the W infinity are. So I agree with you that their standing is a little bit different, but there is
also, it would be there if you have massless matter like photons or massless scalars. You could also define these subleading guys for
I'm not
anything massless. Like they're not special to gravitons.
Oh no. Yes, exactly. I'm not saying.
It's just kind of the first leading ones that are special to gravitons.
It's like solving the gauge field equations of motion order by order in R, and you get an extra integration term. So I agree with, but they're going into the bulk in some sense. Versus the normal asymptotic symmetries, it's like saying like anything that doesn't make it to the boundary is 0. So, sorry. Okay, so maybe I can. I agree. I think I agree with you in principle, but maybe I don't know if I said it in a way that makes it sound like I agree with you. So what I'm just trying to talk about is that the next thing we actually want to do is really talk about these two different notions of infinity and how maybe this space-time picture of them differs. So I didn't go too far into it in this particular talk, but the W infinities, if you wanted to, like, I think the naive thing people were trying to associate it to was like overleading gauge transformations, whether it's a U1 gauge field or whatever, like a Rita-Schwinger field or something, or a graviton. And in that situation, basically, like you have these questions of the phase space versus from the celestial perspective, I would argue that these guys kind of are, I'm going to try to make an argument that basically that these guys are seen by just like the methods of naively trying to apply radial quantization to celestial CFT, in the sense that if I really do have a notion of this BPZ inner product, which was proposed by this, or worked out in more detail by the Andy and friends of the state operator paper. And the reason why it's not obvious is because the hermiticity conditions for the Laurence generators aren't what you would expect for a 2D radial quantized CFT. If one can make that work, then basically one would expect this full tower just from the representations. Not to necessarily say that you expect like the nice symmetry algebras or other operators not to come and ruin this. But basically there's I think the celestial amplitudes perspective prints a cleaner route to looking for these guys in the first place. Versus there's a lot of different questions you could ask from the amplitudes point of view, is like, why would I know about soft limits to all subleading orders? It's like, sorry. Okay. So hopefully that's fine. Okay, so basically now we've encountered two kinds of infinite dimensional symmetry enhancements. The ones where it's like Laurence goes to Virasoro, which is first motivated this program. And then we've talked a bit about these L infinity, W infinity generators, which is this active topic. So the original prediction of the subleading soft theorem and its universality come from connecting these guys to asymptotic symmetries. And what we're just debating right now is related to, can we do the same thing for these guys? Or basically understanding kind of like the bulk picture of what these guys are doing, or why we would expect anything like this W infinity to persist beyond, say, self-dual gravity, where we do understand the origin of the W infinity coming from twistor space and Palatini, I guess, or whoever also some of these stuff. Okay, so we want to understand how bulk quantities behave near the boundary if we really do want to look at like the asymptotic symmetry interpretation of these things, or going into the bulk. So the outgoing radiation is captured near future null infinity, say, and we have this flat metric, and then we have perturbations around it. And the way that one would go about trying to identify the asymptotic symmetries in 4D is you would try to pick a convenient gauge, which is a Bondi gauge here. You would specify physical falloffs, which again are these orders in R contributions, and you might identify residual diffeomorphisms that preserve these falloffs. We can do the same thing in gauge theory. This is not a graviton specific thing, and the same thing with the W infinity. There's other, you do the same thing for other spins, and Monica Pate and others have a nice paper on that. Okay, so basically the original statement, and this is where I think this is where things come into question if we really try to look at the bulk picture of these asymptotic symmetries or these other symmetry generators, is that normally for the asymptotic symmetry group, we look at allowed symmetries, which are the ones that are supposed to preserve these follows, and we mod out by trivial symmetries. And so for the leading soft theorem and the subleading soft theorem in gravity, or like the leading soft theorem in E and M, there's a pretty clear, like this prescription works relatively well. We identify the super translations, which were found by Bondi, Vandenberg, Metzner, back in the 60s. And then so long as we're willing to sacrifice basically being globally defined in the celestial sphere, so we look at asymptotically locally flat spacetimes, we don't mind the sphere metric having a funny like modification at like local points, we get the global Lorentz transformations turning to local CKVs. So these conformal killing vectors now are a function of Z, and then kind of poles at different points in the celestial sphere. And this gives us an infinity of symmetries, this angle-dependent infinity that's much larger than Poincare. And again, basically, there are allowed symmetries because, so for these guys, this is totally fine. They act at the boundary. They're not trivial. They don't change the fall-offs. They're allowed. For these guys, they're allowed because we've allowed basically contact terms in the change of the sphere metric. And they're not trivial because, again, they act at the boundary. So one could, if one tried to find more and more of these, one would be looking at, I guess, either overleading symmetries or subleading symmetries. So they would either get like not be in the numerator or be quotiented in the denominator. And so this is where it seems like at first from the asymptotic symmetry perspective, you're kind of stuck with not the full set of symmetries. Now, for this talk, what I wanted to have fun with a little bit is because I think it's helpful to try to relate what we're doing to ADS-CFT as much as possible. The thing that I want to kind of just have for fun with is this this asymptotic symmetry word identity equals soft theorem was kind of the starting point for this story, because basically we wanted to you have an understanding of why these soft theorems would be universal, because there's this word identity in the bulk that you know, and essentially like the fact that these asymptotic symmetries happen to be parameterized by free functions in the celestial sphere once you're gauge fixing, like that was the motivation for, I guess, looking at like these enhanced symmetries as being representations of something that should live in 2D. So those two are related. But basically, when you wanted to like go through the route of kind of proving these in the first place, there's actually quite a few steps. So normally what one does is one has two Cauchy slices that we push really early times and very late times. And for a Cauchy slice, I'm always going to end near spatial infinity. And so I would look at the charges on one Cauchy slice equated to the other, and basically deform that Cauchy slice to write it in terms of data at scri minus or scri plus, evaluate those charges, use antipodal matching to relate this to, and then use the constraint equations to essentially turn the charges here into flux integrals along scri. And then when I insert the operator into an S matrix, I get the soft theorems as follows. So the key point here is that basically the statement of the word identity is comparing the canonical charge for the in-state and out-state, doing the same transformations that's diagonal on both, and then rewriting each of those in terms of flux integrals along scri to have something where there's a soft part and a hard part that I can identify one as a current and one as a hard matter field. But what I want to point out is that if we now take very seriously that all these extra symmetries we saw in the celestial amplitudes came from like thinking of scattering into boost spaces. Well, what happens when we really do take more seriously the fact that we're using like radial quantization commutators, et cetera, to extract the symmetry algebras and go to the bulk and look at what Windler revolution looks like. And so essentially what I'm doing now is the following. I've just drawn the x1 equals x2 equals 0 plane. And then I want to talk about Rindler time evolution. But what I really mean is not going to be like in this Rindler wedge and this time evolution of a particle that's accelerating. But I want to think about slicing my space-time and looking at a family of slices that are essentially hyperplanes here with space-like normal, and their Rindler time evolution images. So it's going to be a family of basically in this plane, planes that tilt towards the horizon or the other way. And so what's kind of cute about this picture is that basically that hyperplane, instead of, if we replace our Cauchy slice with that type of hyperplane, then we essentially are seeing the soft theorems come out of the canonical charges. And I'm going to look at the U1 case as an example, just so that we can kind of get a better picture of how we're kind of applying techniques for like comparing the bulk and boundary charges, but doing it in a weird way that allows this quotienting by the generator to scry. Okay, so let's start with the easiest slice, which is just x3 equals 0. I'm looking at coordinates near frictional infinity, and I have basically the celestial sphere coordinates will be restricted at x3 equals 0, means that I'm on the equator of the celestial sphere. Now, if I want to look at the foliation of the celestial sphere corresponding to different radial times, basically what I'm doing is looking at the boost images of that slice towards one rim of the horizon and towards the other rim of the horizon. And so that should sweep out. In the bulk, we know you're basically going over towards the North Pole or to the South Pole. And when I look at the Penrose diagram, I really am, one should be a little bit wary of the fact that I don't want to think of everything as being in this x1 equals x2 equals 0 plane. I am essentially sweeping out the full celestial sphere here with these rings. So what I get now is basically any circle on a celestial sphere will correspond to some hyperplane through the origin in Minkowski space with space-like normal. And so basically I'm just doing boost images of this the thing before, but this is useful if I want to think about, say, the support of like 2-to-2 scattering for massless theories is restricted to a celestial circle. This is kind of like a more maybe natural way in which it kind of appears. So in that case, like maybe I don't want to go inside there, but basically what I'm saying is that if I draw a contour on the celestial sphere, I can think of it as deformation of some particular celestial circle, which I know how I want to cut through the bulk in that way. And so when I take, say, a contour on my celestial sphere, and then I allow it to go along the generators of the scry, and I similarly have the same antipodal point on the past infinity celestial sphere, and again go along the generators of the scry there, that basically that surface, if I try to span that in the bulk, will be some deformation of one of these like space-like hyperplanes, for instance. And so if I try to evaluate the canonical charge for my gauge theory on that codimension 1 surface, what I'm basically doing now is like that will be the charge or the 2D theory on like the state on that circle. So that's kind of just a fun way to see how this hologram is a little bit different, but not completely different from maybe what you're more used to, which is like that the charges in the bulk are somehow one higher codimension than in the boundary, versus now our boundary looks like it's codimension 2. And the reason is that basically we have a slice that kind of goes along the generators of scry. And so if I look at the charge that generates the gauge transformation for A mu, and I just look at the lambda times F mu nu, in the standard picture where I look at the charge for like ordinary time evolution, I look at that sphere at infinity. And so it's the FRU components, it's like the electromagnetic field or electric field at infinity, the radioelectric field. By contrast, if I go to this boundary, the contribution near scry is just the radiative fields. So you can see that now the soft theorem, this charge would evaluate to some combination of the two Licity soft theorems on this funny hypersurface. So that's kind of cute that you're already seeing the soft theorem just immediately because of this kind of just jumping directly to that cut of the space-time. And then similarly, the same procedure for like identifying like hard and soft contributions. Just depends how you're trying to deform that surface. You can either keep that boundary fixed and then look at different it's a family of 3 surfaces that span that same boundary. And if you push it all the way to scry, then again, you have a nice relation between static data, so like the external charge configurations and the soft radiation that's emitted. And so basically all I'm saying is that if I want to understand why these soft theorems are generating my asymptotic symmetries, it's because in this radial evolution picture, I'm basically cutting the celestial sphere with a space-like codimension, and I do the same thing in the bulk, and I have that charge. And so in the particular case where I have this current for the U1 case, in 40, there's 2 special things that happen. The 2 helicity soft theorems are related by a shadow transformation, or you can not have to worry about doing anything on local, but you have to add the magnetic dual charge, and you can isolate out a single helicity contribution if you want, strictly speaking, the J that's normally written there. But in the end, basically I'm saying that the state on that circle that I've like transformed with a symmetry generator, I can do the same thing in the bulk, but it's this weird slice that's not a Cauchy slice at all. It's a space-like normal. Okay, so the nice thing about this radial Lickels-Windler picture is that we've kind of jumped directly to the soft operators in the bulk are the ones generating symmetries in the celestial sphere, because again, the canonical charge for that like contour on the celestial sphere lifts to something where it's like a soft operator in the bulk. We've also seen that structure is a little bit nicer in the sense that it's nice to see that it's like the canonical charges in the bulk equals like maybe the charge of an expected boundary. So it's a little bit more like an extrapolate dictionary thing. But again, it's also weird because of this funny notion of the slicings being not a Cauchy slice. Can we further see from this picture with this emphasizing radial evolution that the spaces might be a better way to present the flat space hologram? And so let's do that by briefly taking a step back and looking at different ways of presenting scattering. So the momentum space picture, we Fourier transform, but like we're looking at different like time slices. So like the Hamiltonian is diagonalized. Position space picture is maybe nicer for comparing like the notion of correlators in the boundary to this flat space limit. And the celestial picture is this boost spaces. So the point of the celestial program is basically some of the benefits we've seen is that these soft theorems are directly the canonical charts, and we can see that kind of more quickly from that cut of the bulk and boundary. The in and out come together by notion of just I'm cutting all the way through the bulk. And then if I really take Rindler evolution equals radial evolution, and I say that I can treat it like a radially quantized celestial CFT, which you see in the celestial OPs and whatnot, that people are basically doing that and getting something out of it, then I would expect a decoupling of primary descendants, which would give me this infinite tower of symmetries. And I want to emphasize in the last parts of the talk that is quite a drastic change from how one would try to check universality of like going subleading order in the frequency expansion for this, how the S matrix behaves, or similarly trying to ask about how to augment the phase space with overleading gauge transformations to try to add those symmetries back into the space-time. Now, just to contrast things, so I didn't go too much with the ordinary time evolution case where each of the slices basically ends at spatial infinity, and so you're cutting spatial infinity, like that hyperboloid, into a bunch of time slices, but it always ends on a celestial sphere. If I instead, so it's a sphere that's at I0, if I instead want to look at, say, along the lines of what Reggio et al. And Corellinian people do, they would basically be looking at cuts that asymptote to cuts of U. So like basically the cut into the bulk is not a Cauchy slice anymore, but ends at some cut in U. And you can think about the evolution of operators on that surface. And so these are really extrapolated bulk operators at these boundaries, but now you have basically a strange notion of trying to connect in and out. So you would do this cutting once and you'd have some in surface and you'd have operators and some out surface. You need to basically impose this antipodal matching, which would look kind of acausal, I guess. And you have this null time coordinates. You also have charge non-conservation because things can flux through. And so the notions of the charges that are there aren't conserved because you see that there's a flux balance law. So that is just a kind of contrasting different ways of viewing this flat space hologram. But again, we really are thinking of it as there's this boundary of our conformal compactification where things live, and then how are we looking at it? So positions basis was useful for basically going from the boundary to the bulk, like to basically see that there's an asymptotic symmetry connection, and we can anticipate what the symmetries are going to be because of this knowledge from Bondi, van der Brink, Metzner, and Sachs. Basically identifying those asymptotic symmetries, and any memory effect experiment is more natural in this position basis. But again, is it physical to introduce overleading gauge transformations or even subleading gauge transformations if we wanted to try to find that full tower? Similarly, in momentum space, we're familiar with it just from our understanding of the S matrix. And we can use the asymptotic symmetries in the previous slide to talk about whether or not we expect off theorems to be universal, or to like basically argue that they have to have this nice form. But how far subleading can we go? And that was Simone Karen-Holt's question. And again, if I just strictly speaking say that I can do radial quantization, just like push that that 2D perspective more, then I would expect, for instance, that I have basically a series of primary descendants because I have this 3 manifold. So what I'm saying is that I have this continuous set of conformal dimensions that now I am free to tune. And so I can always tune it to a value of delta, at least in the case where I'm in, it's easy to classify the primary descendants for this 2D theory. So I can always tune the value of delta such that I land on one of these primary descendants. And so now if I have like an OPE that's a function of delta and it's supposed to be analytic in it, then essentially I have more control over this thing, because basically so essentially I can go to a value of delta where I know they have this primary, the primary descendant. And if I further say that the primary descendant must decouple, which we see that it does, but it's not obvious necessarily from the hermiticity conditions for what we expect for the BPZ inner product versus the ordinary 4D Hilbert space, the Laurence generators on it, that basically I would expect a tower of currents, at least in the sense of like these truncated shortened multiplets. And now further, because those obey some symmetry algebra that they should constrain when I try to lift it to functions for the OPs that are a function of like an analytic function of the conformal dimensions, for instance. And now I know that the values at certain limits, those residues have to match onto the ones where they have these interesting symmetry constraints. So that's the kind of the structure of how, what I wanted to say was the benefit of looking at this celestial slicing of this boundary. So basically,
can I ask a question?
Yeah.
So the words that you were saying on the previous slide
Yeah.
are reminiscent of words you say when you construct minimal models by, I don't know, asking that representations, Virasoro representations decouple. Is that like just similar sounding words, or is there like?
I mean, I would love it if it weren't just similar sounding words. I'm not sure if I'm a master of the other side of it to say that. I mean, right? Like I think if I were Andy, I would say no, they're like related, you know. But I'm not going to go that far. But so I guess I don't know if I have a good intuition for maybe why you would expect, like, if there's any sort of tunability of that parameter, like that's class of things is interesting as opposed to just the tuned limit, if that makes sense.
Okay.
Yeah, I don't know. I mean, it would be very interesting, and I want to say that there probably something deeper there, but I don't know if I think if I said yes, then I would be challenged. I should be challenged for it. Like, yeah. So,
Okay.
Yeah.
Thanks.
Okay. So basically what what I'm saying here is, I mean, I do kind of believe though that there's going to be a sense in which we can like you write they say the 2-point functions for this continuous spectra of dimensions should give you some like generalized free field. And then I think that if I look at that like Gaussian theory, that there's this limit sense in which if I take the limits, like the Green's function, there's this like the 2-point functions become like Green's functions for different descendancy relations at these integer values of the conformal dimension. So I think there's a sense in which hopefully there's some pole that I can extract and I can really write this 3D looking theory in terms of a sum over 2D looking modes with basically higher derivative kinetic operators that would capture. So I think there's going to be a sense in which maybe we land in a tower of like a large tower of modes that is somewhat more 2D like instead of 3D like, but I don't know if there's a sense in which I would tune to like a particular like a subalgebra that I guess I don't know if the right phrase. Okay, so the what I want to just close on is that the purported advantage of the celestial holography program is this reorganizing scattering in terms of symmetries. Now, originally that really meant the soft theorem asymptotic symmetry, so the infinity and the angle dependence in the night sky from the known asymptotic symmetry group. And then when you go to the celestial basis, you encounter a bunch of conformally soft modes that seem to have interesting OPEs and algebras there. And those additional symmetries, because of those radial quantized commutators, should impose interesting constraints in the S matrix. Now, to what extent you can extend that just from a single helicity sector to more generally is, I guess, still under debate. But in the end, right, we're trying to bootstrap, or we want to eventually bootstrap amplitudes from collinear limits. And one thing we can do already is we can use like this, say, the subleading soft photon theorem or subleading soft graviton theorem to really get a recursion relation. So this lovely paper by Pate, Yuan, and Andy and Anna shows that you can solve for these OPE coefficients as a function of the conformal dimension from like one extra subleading soft theorem. And I think that result is really beautiful because it's the first kind of thing that's bootstrapped like. But what I want to emphasize for this talk is, again, that radial quantization was playing a crucial role in most of these steps. And so it's obvious in this step and in this step from the way that W infinity were realized. But the point of this talk was to say this also here in this step. So thank you guys for listening to me and for the lovely questions. And I'm happy to debate anything.
Yeah, thank you very much, Sabrina, for the very interesting talk. And so I already see hands raised, so let's not delay questions. So Robert?
Yeah, so are you making any assumption for what is in the center of this space?
I mean, like literally, like, yes. So I am making assumption right now.
I'm heading to the question of whether you can apply the formalism to understanding the decay of a black hole.
Yes. So right now I have basically not included a horizon component. Sorry, like I guess I really don't need a Penrose diagram, but I guess I will just try to find it. Okay. So I have written everything where I don't assume that there's an extra external horizon component. I think that if you wanted it to evaporate and so that like the asymptotic boundary really is described, then things should be okay. But again, I am yes. So I would say that celestial CFT, the attitude would be, yes, we can include like a black hole in the space-time, so long as we assume it evaporates, and so that these are the only asymptotic boundaries. It should, in principle, we want a hologram that lives at scry, and we would think if the S matrix is unitary, then that would include everything. And so everything that I've been doing really has, I think, been restricted to the boundaries. One could ask questions about certain like antipodal matching conditions or whatnot if I do something really weird in the bulk, but I think that everything I've said should be living in some, like, I can write everything in terms of some sort of neighborhood of the conformal boundary. I know I do a plane through the space-time, but I could have deformed it away.
Yeah, so let me modify my question. So instead of taking a black hole, let me take a spherically symmetric star. Just something that in the absence of nonlinear effects would be static.
Yeah.
And then can you use your formalism to somehow understand how this star will emit stuff that escapes to infinity? So essentially you have scattering of massless stuff, but in the presence of something in the center which is made out of massive stuff.
Okay, so the thing that so like basically the thing that I'm wearing, okay, so I think I would normally, like if I had some sort of inspiraling binary system, which I guess one could say is not really like I don't normally view it as going out to infinity, then I definitely can say something about how the soft theorems would measure like angular momentum that's radiated. There is a sense in which, strictly speaking, if I use these word identities, I say soft equals hard, then I can, if I know that there's then, like, sorry, what I'm saying is that I can implement a change in the kinematics and compensate that by saying there's extra soft radiation. But I don't think that that necessarily is useful to the extent that you care about it. But like I think the closest thing, yeah, no, I think the extent to which I thought about a problem like that is not very useful. It's more just like if I did try to do a VCFW shift or something like that, and I try to deform the external kinematics, can I equate that to having added just soft radiation instead? And so that kind of is a similar spirit in the sense that you're taking a system and you're trying to modify it, and then you're saying that's equal to something else. But I don't know that it's not quite predicting like whatever, some deformation of this compact system that has some sort of non-trivial interactions with the gauge fields or something. I don't know how I would set that up, but the chance of you being able to set up something where you could try to shuffle around Q soft equals Q hard in a way that I think maybe someone could make mileage with it, but I don't have something concrete more to add there, right?
Yeah, thanks.
Yeah. Yeah, because you had no radiation whatsoever, which is really unphysical. This is but if you had some sort of scattering process where there's no radiation, and then you wanted to modify the in and out kinematics of that, you would then see that there would be, you could say that that's equal to adding soft radiation. So I think there's something there, but that's not. Yeah. Any further questions, Simon?
Yep.
Hi. Yeah, thanks for the nice talk. I have maybe I'll start with the more technical one, and then I have another questions. So the commutator you described is from radial quantization. In principle, there's another commutator one could imagine taking. It's like you take one graviton much softer than the other, and then you take that in different orders. Which one is softer? Is that, are these notions of commutators related, or are they distinct, or what?
Okay, so that's when you take it soft. So the question is that there is a sense in which for these, okay, we want soft and collinear limits to commute, and maybe that's not a good thing to ask. How do you feel about saying that statement? because so what I mean by that is the following. So let's take a step back and maybe like not answer your question, but use something where assuming that soft and collinear limits commute has led to equations that like bootstrap the MHP sector.
Okay, if you assume that they commute, then okay, you get some commutator equation.
Yeah. So what I mean to say,
way. But technically, your calculation is about commuting the collinear limits, right?
My computation is about commuting collinear limits. So you think the computation is collinear limits. But what I did want to say is if the soft and collinear limits commuting leads to these Banerjee-Ghosh equations, for instance, that people have been using to solve Celestion. So maybe if you could reverse engineer that and say that no, I don't want to assume like, sorry, but I guess I was trying to understand is if there was a way to get to what you were saying and relate it to the radial operator algebra by tracking through that assumption. But
in principle, it's the radial algebra, and it's
yes,
so.
yes,
Do you know? Is it known that it's the same as the soft algebra, or can it be different?
so I want to say that at least at the lead. Okay, so so people have checked that they can define these operators that include like quadratic terms. So it's like the soft operator, like domain Ricconi, that obey the correct algebra that we expect for, say, the super rotations. And so there's a sense in which that requires understanding the soft limit for like quadratic terms, which seems like a double soft limit, but that's not the same thing as this technically like double soft commutators or anything like that. So the thing that I guess I'm confused about is if I want to do a double soft limit, that should basically be whether or not the order of limits matters when I take conformal dimensions, like to go to one pole versus the other pole is what I'm saying. So if I have two, basically the question would come down to whether or not when I write down these expansions for whatever, maybe instead of a beta function, I leave a C here, that extracting the residue in delta 2 versus in delta 1 or vice versa is a problem or not, because that's what this soft limit commutator would mean.
Yeah.
So I guess I haven't played with it enough to basically say something there. I wouldn't be surprised if there was some sort of subtlety in other contexts for that, because I'm just thinking about, I would want to go through the references from I think like Sharma and Adamo and Lionel before I would say something stronger there, because we do run into a lot of orders limits issues with like soft limits and radial limits. So I don't want to overstep there, but it would be a different commutator. It would be literally the statement of whether or not these functions have a well-defined like double soft limit, rather than that the operator algebra itself, like for generic delta, is okay. So, but that is important if you want to look at the algebra for instance, these residues, right? Because that's how you would extract them. But I think that I don't want to say something I don't know the right answer to. Yeah. But yeah, it's a separate question, but it's an important question for the same problem of going from this guy to these guys. So,
okay, I have a kind of more general question, which is okay. These soft theorems and these symmetries, they tell us what soft gravitons do. They give us a soft graviton wave function in terms of what mostly what the hard guys do, and some expansion and so on. Is the goal of looking at these higher moments to study like finite energy graviton? Or, I mean, what exactly are they going to be used for?
So I think that I would say that the hope is the following: is that if we can, okay, so it's like a combination of I guess the kind of perspective that's in Cunningham et al., even though that's looking at like the internal conformal dimensions versus this is like external conformal dimensions. If there was a way that we can understand that all of the poles in delta are like one side of the principal series, and like we understand the analytic structure of the amplitudes in the conformal dimension, and that there aren't like branch cuts or anything like that, we can really like think about deforming that contour and picking up poles there. There might be a sense in which that tower of soft modes would be like somehow like there'd be a theory with just those guys that would effectively account for the full thing. I think that's a little bit optimistic, but I think that's basically saying that we're going to use these like basically Taylor series expansion in the soft limit to capture all of scattering, which sounds a little bit strange, but then again,
it seems to be mixing a bit two different things. What I'm confused about is that the input here is that the poles are only on one side. There's some idea that maybe at high energies the amplitude decay exponentially or something like that.
Yes.
That's a very non-persuasive statement. Yeah. And on the other hand, here you're putting this commutator algebra you're discussing very perturbative.
Yes. No, I agree with. Okay, so I agree that
it sounds a bit. It would be a bit shocking that using some perturbative algebra combined with this non-perturbative constraints, you will be able to construct the whole thing exactly.
Okay, sorry. So I agree. Sorry. So let me think if I want to say that we hope that versus that we think that. So like, okay, I think it's reasonable to try to at least consider what would happen if we like can exclude, like basically use some sort of argument for how the paper is at infinity to get rid of poles on one half plane, and then look at the operators in these and see if that makes sense. Like, I mean, so I am basically saying that that's, I think, what people are saying. So I'm asserting that what your summary is what people are hoping to try to do. And then now we can debate whether or not that even seems reasonable. I'm fine with trying to debate that. Okay, so so I think I agree with you that it's not clear that you want to just like use the tree level. Like, I mean, there's a lot of tree level OBs being used, and that's not good. You want to go to like higher loop order, or even, or should be worried about can you compute it in perturbation theory, et cetera. But so maybe to take a more like, and I don't know how to set this up necessarily, but if I really did want to say that I know that those collinear limits are going to be the data of this theory, and that I really want the poles where I think they should be, then I could try to maybe to set up a program where I'm bootstrapping those CIJKs, which then wouldn't rely on their perturbative values. But maybe that's very optimistic and a little bit far-fetched. But I think in principle, I think there's something like, I think the locations of the pole seem somewhat stable, but can you object to that, or like, so that, I mean, I'm happy to, I want to hear your guys' take on that too, because it's valuable for what we do in the future. I
really don't, I don't know.
Yeah, no, I want to basically say that I want residues at certain values of the conformal dimension that I expect from this.
I mean, at some point, the very high residues you probably cannot compute perturbatively anyway, because
yes, but I
when
want
quantum numbers become large, perturbation theory is not great.
Yeah.
At some point, like, you don't no longer trust tree level physics.
Yes.
As soon as you start probing what's happening inside the scattering process, like, you don't really trust.
Yeah, but I want to say that basically I want to trust just that those values of the conformal dimension are special from just a representation theory point of view, and that I know that at perturbation theory they give me poles. And so to what extent can I ask the question, like, could I phrase a question where I say that those are the only poles, try to find some sort of consistent, like, yeah.
But again, that's what I don't see. The first few I can see they're special, and maybe they're computed.
But the commutators,
the consistency of the algebra and so on. But the poles that correspond to very high multiple moments, it's not clear to me. It seems surprising that you can compute them without somehow figure out the detail of the scattering process that happens in the middle.
Sure, but the question is, I don't know if I want to say. I think what I want to ask is more like. Okay, let me try to think if I can say this. So I think there's a tension of whether or not that soft graviton mode equals something that I know the answer to for like other hard modes, right? So in the leading cases, I know that like the stress tensor is equal to, because of the constraining equation, some matter field in this theory. I'm not sure how much I want to push. Okay, so I agree with, okay, so then your question is basically the algebra of those operators going on, like, if that persists or not. I think that there's definitely some fun that one can play with trying to push that further, and that I think the Bolovich group is going to like look at different interaction terms and see if they mess up the W infinity algebra or not. But I agree with you that you can't use that as a reason to kill things, because it's not like something necessarily very physical. It's just this algebra that you see at tree level or you see in the still sector yet. But okay, so I still think that so for me, I think the more important thing is just the fact that there are these, like, where the poles are in this conformal dimension, like in delta, and then some sort of closure of that, and trying to push that further, rather than, I don't care so much about the W infinity story personally. Some people are more invested in it than others, but I care about understanding the fact that there is this tower of decoupled primary descendants, these shortened multiplets.
Okay, but the goal of something that, for example, you might like to compute is something that represents like graviton scattering at infinite energies with some background process. What would be the background process?
So I don't know if I want it. I don't know if I would phrase it that way, or just try to find a constraint on the data, like try to phrase like some S matrix bootstrap like program in terms of constraints on this residues here. Like, so I think I don't know if I would.
I guess my question is maybe let me ask this from something coming from outside. Like
yes.
Suppose you succeed and you manage to compute all these residues.
Yeah.
Like, what can I compare them against?
You would know. So like hopefully then you go from the residues to the amplitude at various conformal dimensions, like and all conformal dimensions, and you go back down and you go from the residues to the principal series, and then you Mellin transform back to the amplitude. And so like you would say that that's the amplitude. Sorry.
Yeah. Okay. Yeah. But that would be for some specific process or something like that.
I mean, I guess it's more a family of processes, which is by nature of the fact that you're kind of summing over all energy scales. But so I guess maybe the question is to you, when you say specific process, you're thinking about like scattering in some, I mean, so definitely.
Anyway, I'm wondering if you're imagining states where you have like a planet in the middle or a black hole, or maybe like more like, I don't know, scattering of electrons at the electron collider, or like what you're looking graviton emitted by what?
Yeah, sure. But I think that so that the thing is, I'm not sure if it's clear in this setup that there's the backgrounds that you're scattering in are the natural way of thinking about. Like, I think I'm just literally thinking of some S matrix process. So I agree with you that if I'm looking at, say, like certain graviton modes, and I'm looking at graviton scattering, or if I'm looking at, say, a gauge theory, like basically like the operator content coming from a different spin in the bulk, then I'm looking at some other S matrix problem. But I don't know if I would say that I'm setting anything up right now to talk about like scattering in a different background, for instance. Like, so I would say that the data that I would have would just be some S matrix element for whatever subset of the external particles species that I've like focused on, I guess.
Okay, no, that's
so whether or not it's closed or something under, yeah.
Okay, so for example, the 2 to 3, 2 to 2, or 2 to 4, so the S matrix amplitude with just a few gravitons, that would be interesting for you.
Yeah. So for instance, like, so yeah, in that situation, I'd basically be trying to like identify the correct CIJKs and do like just a conformal block decomposition for those, assuming that you can get all these funny details with like the work.
2 to 2 scattering also interesting, or it's too trivial in this?
So 2 to 2 scattering, I mean, it's interesting in the sense that basically at 2 to 2 in massless theories, you have these constraints in the celestial sphere. So there's a little bit of work.
You can't really take one guy's stuff though.
Yeah. But there's a way to kind of resolve it by changing your basis. And then you can see this, the OP coefficients are the 3-point functions in a slightly smeared version of things, which is nicer. But then again, I think there's still work to be done. We're working on a conformal block decomposition in like these light transform states where the 3-point is nice, but the goal is is to try to like basically organize the S matrix in terms of a like CFT data, and to understand the CFT data and to constrain it based on not just on W infinity symmetry, but probably more hopefully on like locations of where poles have to be from like some sort of dimension counting, and then hopefully causality, and like we're going to basically be like lifting off of S matrix bootstrap techniques.
That's good.
Yeah. Sorry.
That's good.
Can I ask a naive question?
Yeah.
So every time I hear a talk like this, where you try and organize things in a 2D CFT language and you introduce Virasoro algebras, I'm required to ask about the central charge. What is the status of?
Okay, the status of the central charge is that I think it's IR cutoff dependent.
Because there's no dimensionless parameter, right?
Yes,
so there has to be. So it's like Newton's constant in units of an IR cutoff.
So I think that we wrote it down in this paper with Herman. I guess it's it's Newton's constant in the unit of the IR cutoff, roughly whatever dimensionless quantity you're getting there. And it's coming, the nicest way to see it, I think, is to think of regulating, like, so you cut off at a surface like x squared equals cutoff squared for plus or minus for the tube thing. And then you basically get, say, 2 Virasaurs acting on these large hyperboloids. And so it turns out that you can basically deform, if you can slightly deform the algebra you get between the Goldstone modes and the charges, you can get kind of 2 stress tensors with complex conjugated infinites, like there's this parameter that you want to go to 0, which have this like central charge that is complex and like 1 over epsilon. So it's a funny, it's definitely something where I think you need to understand the role of the IR cutoff to even start talking about having a non-zero central charge. And then that's why I tried. So part of the motivation for this talk, even though I avoided that discussion here, is to like kind of try to relate everything we're doing to how we would do it in an ADS context, because in that, I think if you understand the flat space limit a little bit better, maybe we can see how these algebras get deformed by, for instance, the operators one would have in a ADS background. So that's one hope there. But yeah, so the central charge is a function of the IR cutoff in any sort of, I think, way of trying to get a non-zero one.
Yeah. Okay.
So, yeah.
Or not infinity. It's yeah. As you take the IR cutoff away, does it go to zero? Infinity? Sorry.
Infinity. Yeah.
Okay.
The way that we constructed it, but
so
maybe that was a little artificial. We tried it. We wanted it.
Is it possible that like the actual algebra is a contraction of the Virasoro algebra or something like that?
So we wrote down.
No,
yes.
Yeah.
So that's exactly what we. Okay. So with Herman though, I feel like we did it a little bit speculatively because we wanted to land on, like, we knew what we wanted to land on at some level. So like, I think it's okay to do this, but it is a little bit like, what I want to do is basically try to look at the algebra one gets if you assume a ADS background instead of a flat background, and then see why that contraction is a natural one. Because basically you have this kind of overcounting of modes in some sense. You have like these Goldstone modes that are symplectically paired to their memory modes.
Sorry, in this case, your IR cutoff is ADS bound, is ADS.
I would think so. In that context, IR cutoff is like an ADS3 like radius scale, but I think that the more natural one would be ADS4, which we haven't talked about. So the construction that I mentioned, which is basically I add a small deformation of the algebra, and then the one that I actually see in flat space is a Nuno-Wigner contraction of it. That agrees with this picture of capping off the space-time with these ADS3 cuts with a certain curvature radius. But I think the more covariant thing would be to basically like change your background from flat to ADS. And that will change some of the allowed interaction terms, which would modify the celestial symmetry algebras that one would get in the same procedure. So I would like to see that extra term that we added by hand to match this two cutoff ADS3 CFT2 picture they had to come from or how it comes from a curved 4D background, but
okay.
But I don't know.
Okay.
I don't have an answer. I just have a proposal for the contraction.
Yeah. No, that's clear. Thank you.
Thank you.
Okay. Yeah. So thanks for the discussion. I don't know if there's any final question or comment. If not, I think we can stop here. Thank you very much, Sabrina.